All yours, people. Clock just ticked over. You're fine. Well, I mean, that's just because our biometrics aren't good enough. It won't scan your retina at this point.
Sure.
You know, you just do this.
About
Did you see the movie Minority Report?
yeah.
Quite literally, that is the way AI works in that setting. That as people wander around, there are cameras in the billboards. And if they catch you looking at it, the actor on the billboard focuses on you and says something targeted to you.
Well,
So they're really watching people's eyes all the time. But that means you use them for biometric identification. So literally, in order to break into someone's house, Tom Cruise's character has his eyes replaced and then keeps his old ones in a cryovac bag so he can still use them to get into places.
I saw that. Like I saw it.
There are a number of places where you biometric data is you know, you need somebody's handprint.
Yeah.
So they chop his hand off and take it. Lifting fingerprints is a common practice nowadays to falsify identification like that. I'm waiting to figure out how to lift eye prints.
Yeah, like National Treasure.
Sure, they did it a bunch of places. They do it downstairs. The forensics lab lifts fingerprints.
Oh.
It's one of the classroom activities. They have mine. I gave them to them for a lab.
Did they technically do like FBI documentation? Then I like you guys system to the forensic lab do that? Yeah.
Not here. We're not an FBI center. I think Dr. Flowers does have connections, though. But this technically is a differential equations class, not a forensic science class. So what questions do you have about this course? Chapter 8, sections 1, 2, and 3, or the exam on Monday.
So for 8.3, when we're doing variation of parameters, then we take the integral of the,
Phi of t
yeah,
times f of t. Phi inverse of t
yeah,
times f of t.
we don't need a plus.
Correct. Because we're assuming that plus c is going to show up in the c1 times the xc part. So I don't have to worry about that part. That's the same issue we had when we did variations of parameter back in chapter 4. We were allowed to say, oh, I'm going to let it be 0 here, and I'm going to let it be 1 here. I'm going to make an assumption about the plus c that I would normally get and just roll with it. Isn't it? Somebody talk to me, please. Yes, ma'am. I hope so. 8.223 has repeated eigenvalues, sorry. So 23, -1, 3, -3, 5. So let's do the eigenvalues to start with. A minus lambda I is -1 minus lambda 3, -3, 5 minus lambda. So when I do the determinant of that, -1 minus lambda times 5 minus lambda minus a -3 gives me a +9. Lambda squared minus 5 lambda plus 1 lambda minus 4 lambda. Minus 5 plus 9 is +4. Wait a minute, that's lambda minus 2 quantity squared. Okay. Thing 1, I need an eigenvector. So I put in lambda equals 2 up here. -1 minus 2 is -3. 5 minus 2 is 3. Set that equal to 0, 0. Do my reduced row echelon form. And I get 1, -1, 0, 0, 0, 0. I am going to do this routinely. I just realized I did it right here. I start to write these in parentheses because that's the way the book writes them. And then I start to think like I'm in linear and I start to write them with square brackets for matrices. So you'll notice I have a square bracket and a parentheses. I don't care. Okay. That means that x1 minus x2 is 0. x1 equals x2. I have 1, 1. Now, how do I get the next eigenvector? This is where I need to follow the idea in the text on page 360, where I take the vector we got from the first solution, that's line 13, and I replace it on the other side. So instead of being 0, 0, it'll be 1, 1 here. So the generalized eigenvector now looks like this. Oh, I get this. And so I get x1 is x2 minus a third. With me so far? Now, how do I make this do the repeated eigenvector thingy? You might think that the thing I want to do is keep them like that together, right? Write it as 2/3, 1. There should be a line there. Right? Yes. So I did that here, right? P1 equals P2 plus a third. I just used X instead of P.
That's like added on to. On,
That's the first part, right? The second part is 1 e to the t e to the 2t. Now here's where you get a choice. I put in 1, right? For the x1 and x2. Sorry, put in 1 for x2. But what if I'd put in 0 for x2? Sorry, p2. Then this would be negative 1/3, wouldn't it? So I can use either of these vectors. That's my extra bit. Maybe?
Yeah.
So is it safe to assume that like the first vector, first pair of vectors was like what it would equal to, I guess? Like the 1, 1 vector pair 1, 1.
Mm-hmm.
That's always going to be,
That's in both of them.
but like to skip this second, it's always going to be equal to.
Yes. That's exactly how I got this here. It comes from that right there.
So say like 2, 5.
It'd be 2, 5. Yes. Because what I'm asking is, all right, what else goes this way, but also has this extra bit? And that's the generalized eigenvector piece that we're getting. Now, what this really gives me is it gives me one line. The line 1, 1, right? So instead of having 2 sets of arrows, I have 1. And it's e to the 2t, so we're going out at 45 degrees, right? So if I were to draw a phase portrait, my first reaction is that what I should see has this line at 45 degrees, and we're going out along that direction, yes? Which means everything else should be spiraling out with this little extra twist coming away from 0. There's a better picture because I'm a crap artist. Here on page 361. This one's coming in because it's e to the minus 3t instead of e to the positive 2t. I'm ad-libbing. There is, in one of the other textbooks I have downstairs, there's a classification, and it calls these sorts of spirals out and in. If you're going out, it's a source. If you're coming in, it's a sink. So this would be a spiral source, but it still has that one line on it, right? So it's a half spiral, or sometimes a barred spiral, which happens to be a term they stole from the astronomy people, because that's a type of galaxy. More questions?
Do a random example.
Sure, a random example. Let me pull one from the text because I'd be hard pressed to make one up and make sure it was complex. Um, let's do 35 because it says right there that should have complex eigenvalues. Okay, 35. Six negative 152. 6 negative 152. X prime equals that X. So I need my eigenvalues. A minus lambda I. 6 minus lambda minus 1 5, 2 minus lambda. So 6 minus lambda times 2 minus lambda minus a negative becomes plus 5. So I get lambda squared minus 2 lambda minus 6 lambda is minus 8 lambda plus 12 plus 5 is plus 17. So far, so good? Okay. Wait a second. Lambda squared minus 8 lambda plus 16 plus 1. Why 16? Because that's half of 8 squared. That's the completed square. That makes this lambda minus 4 squared plus 1. When I go to do the roots, lambda minus 4 squared plus 1 equals 0. Lambda minus 4 squared equals negative 1. So I get lambda minus 4 equals plus or minus I. Lambda is 4 plus I or 4 minus I. Okay, there are my values. Here comes the crap part. I got to put those back in here. So when I go to do the row reduction, I'm going to be looking at something ugly. Lambda equals 4 plus I means I get 6 minus lambda, so that's 2 minus I, because it's 6 minus 4. Negative 1, 5. 2 minus 4 is negative 2 minus I. Oh, wait, there should be a bar, 0, 0, and then the brackets. If I really want to do all the row reductions, I should multiply by something and add them and all of that stuff. Blech. The whole purpose was that this gave me a determinant to 0. If I know this is going to give me a determinant to 0, then I know the top row is going to cancel the bottom row. If I know that already, then I can just pick which row I want to use, the top row or the bottom row, and use it. Okay, then I'm going to write 2 plus I times x1 minus x2 equals 0.
Why is it plus?
Oh, because I made a copy error. It's 2 minus I. It shouldn't be 2 plus I. Read the problem correctly, Joshua. Whoops. Okay. So that means that x2 is equal to 2 minus I times x1. I might as well let x1 be 1, and then x2 will be 2 minus I. Here's the interesting part. You can actually do the calculation over there. Because if you take this top row and do 2 plus I times 2 minus I, you get 4 plus 2I minus 2I minus negative 1, you get 5. So you can actually figure out what to multiply by to cancel that row out. You could do it if you really wanted to. I don't. I don't think anybody really should. If we had a 3 by 3 and there were complex numbers in a 3 by 3, I'd have to. Shoot me now. I don't want to do it. Okay. So now, technically, I could do the other one, but I know that if this is all real numbers up here, and this was all real numbers in the matrix to begin with, then when I do lambda equals 4 minus I, I'm going to get 1, 2 plus I. If the roots are conjugate and all the coefficients up there were real, so is the I. But I really only need one of them. Because what I'm going to do now is I'm going to write the answer. I'm going to write vector times e to the eigenvalue t. That's the right answer. Problem is that it's got I in it and I sucks. So what do? Into, right? And e to the it becomes,
Cosine BT plus I sine.
but bt is a 1 here. So it's just cosine t sine t. So I now have 1, 2 minus I. I'm going to leave the e to the 4t alone. I'm not even going to mess with it. I'm just going to leave it out front. Cosine t plus I sine t. What I need to do is multiply that the cosine and sine part into the vector. So we're going to leave the e to the 4t alone. Multiply this by 1, I get cosine t plus I sine t. That's the top row of my vector. But the bottom row of my vector is 2 minus I times cosine t plus I sine t. And now I need to multiply all that out.
So if, or, if like, it's 3i,
Where?
but,
Here or here?
2 minus, say it's 2 minus 3i.
Then it would be 2 minus 3i right here.
But there, you have 3i.
Oh,
Or no, just,
no. This came from here, right?
what if that was?
Then I would have it.
Then it'd be
The 3t and a 3t. Yes. Because what I would do is I would think of it if it was lambda was 4 plus 3i, I'd write e to the 4t and e to the I 3t. See how the I part is separate? Then it would be cosine of 3t and sine of 3t. Yes, that's where the beta comes from.
and then it would just be the I sine.
Uh-huh. Yeah, the only thing that would change would be the 3t here and here. Let's multiply this out. Two cosine t minus I cosine t plus 2i sine t minus I times plus I is minus I squared. That's minus a minus 1. That's plus 1. Sine t. Now here's where my bias against complex numbers in differential equations shows up. Take all the stuff that has I in it, put it on one side, put everything that doesn't have an I on the other side, and then we're going to split it into two pieces. With me so far? I haven't actually split it up yet, but I've written it where all of the real pieces are in the first half of the lines and all of the imaginary pieces are in the second half of the lines. So my solution becomes C1 e to the 4t, just the real parts, cosine t, 2 cosine t plus sine t, plus C2 e to the 4t. Drop the I. Sine t minus cosine t plus 2 sine t. That's how you split up the complex stuff into not complex stuff.
Now, when you multiply the I by I, you get negative.
I times I is negative 1.
Would there be any case where it's not negative 1?
No. I times I is always negative 1. That's the definition of I, because that's how we got it in the first place. We said that, oh, when I did the lambda minus 4 squared equals negative 1, I took a square root. So lambda minus 4 is plus or minus the square root of negative 1. And that's our definition of I.
What if it was like negative 4? Then it'd be.
It'd be 2I, right? It was negative 17. It'd be square root of 17. I.
Yeah.
The negative part is what gets pulled out. Complex numbers are your friend. Most of the time. Like, which one? 8.114. Write it as a first order. So let's do 13 or 15.
Let's do. I'm not even looking at it, so it's just.
Oh, okay. 15 says,
Let's do 13.
yeah. Okay. 13 says y double prime plus 4y equals t cosine t. Okay. My replacement to write something from higher order down to a system of first orders means I want something to replace y and y prime and every other derivative up to the highest derivative. In this case, that's only the second derivative. So I really need something to replace y and y prime and stop there. So let's pick two variables, right? X1 and X2. But X2 is X1 prime, which is the same as Y prime, isn't it? And that means that X2 prime is Y double prime. Now, here's the sneaky part. This right here, that's one of my equations because it tells me about X1 and how it's related to X2. Yes? Let's look at this equation. This equation is about Y double prime. Let's write Y double prime alone. So it'll be minus 4y plus t cosine t. Yes? But y is x1. And y double prime is x2 prime. So this equation just became x2 prime equals minus 4x1, no x2's, t cosine t. Now take this equation, add it into the game, x1 prime equals x2. That's a system. Now, normally we'd write x1 prime on top. And then we'd write x2 prime on the bottom. I could even turn this into a matrix if you wanted. I could write it like x prime equals 0, 1, negative 4, 0, x plus 0, t cosine t. There's my non-homogeneous system of equations. The whole idea is to replace everything except the highest derivative with a new variable and write the relationships between those variables. Better? Right. It is for this reason that higher order differential equations often get short shift and people don't pay them a lot of attention because it's a lot easier just to make it a system of first order differential equations. Problem is that, I'd much rather solve the second order differential equation in this case because I'm going to get complex numbers and a t cosine t. I can use undetermined coefficients to get. It's easier than doing it down here with the, how did Mia put it? The integral of the phi inverse f. Yeah, and I don't want to do that stuff. That's disgusting. I could do this the easy way if I left it as a second order. But it works to solve it this way. It's also gross. More questions? Yes, Jay. 8.317. I hope so. (8.317) x prime equals 0 to negative 1, 3 x plus 1, 1 e to the t. Oh, 1, negative 1. Okay. It wants me to use variation of parameters. This is the long way. So we start by solving the homogeneous version. I need eigenvalues and eigenvectors for that matrix. Fortunately for me, that's straightforward. So when lambda is 1, I get 1, negative 2, 1, negative 2, 0, 0. My reduced row echelon form, the rows cancel out. x1 minus 2x2 equals 0. So x1 is 2x2. The vector in question is 2, 1. If lambda is 2, I'm going to get this. Because the top row gets canceled exactly, and I swap them out. So I get x1 minus x2 is 0. So x1 is equal to x2. And the vector in this case is 1, 1. Wonderful, beautiful, perfect. C1, 2, 1, e to the t, plus C2, 1, 1, e to the 2t. That's also how I make my fundamental matrix, that phi of t. Phi of t is 2e to the t, 1e to the t, 1e to the 2t, 1e to the 2t. It's the matrix whose columns are my two solutions. I need the inverse of this. Okay, this is where I'm going to make my question again. I got to switch 2 and put minus signs on 2. It's 1 over AD minus BC. And then it's the adjoint. So it's DA minus B minus C. Right? Then I'm going to do the transpose. I think that's right. The adjoint formula, and I can never remember it. I always have to rederive it. You remember it? Good. I'm glad. But somebody has to remember it. It's better that way. Okay. AD minus BC is 2 e to the 3t minus 1 e to the 3t. And then I switch those two. So it's e to the 2t, 2 e to the t. I put minuses on these two. But this is e to the 3t on the bottom, right? Which is really e to the minus 3t. So let's multiply that in, and I get e to the minus t, negative e to the, oh, wait a minute. Yeah, minus t again. Then here I get minus e to the minus 2t, and here I get 2 e to the minus 2t. Bleh. I'm partway done. Because now what I do is I take phi inverse. This is why I write the formulas down for these. It's phi inverse times f of t. So I'm going to take this matrix and I'm going to multiply it by the other one that was on the end added to our setup. So e to the negative t minus e to the negative t, negative e to the negative 2t, 2e to the negative 2t, times, what was the added on piece? Up we scroll. That's this piece here. E to the t, negative e to the t. And I get, wait a minute, I get e to the 0. That's a 1 plus another 1. I get negative e to the negative t minus 2e to the negative t. So I get 2 and then negative 3e to the negative t. Right? Whew. Here's the fun part. I need to integrate that. Integrate. Phi inverse of t, f of t, dt. Well, that's really just doing two integrals. What's the integral of 2? Oh, I like that part. What's the integral of e to the minus t? So that this minus sign will cancel, and I'll get 3e to the minus t. I'm almost done. I now need to multiply by the original phi matrix. Phi times that thing. The original phi matrix. Glad we wrote it down. Two e to the t, e to the 2t, 1 e to the t, 1 e to the 2t, times 2t, 3e to the minus t. So I get 4t e to the t plus 3 e to the t. Or 4t plus 3 e to the t. Down here, I get 2t e to the t plus, again, 3e to the t. 2t plus 3 e to the t. This is my particular solution. Holy crap, we did it. Wait a minute. We did it. Ready? It is x equals C1, 2, 1 e to the t plus C2, 1, 1 e to the 2t plus this. 4t plus 3, 2t plus 3 e to the t. You ready for the crazy part? Why does this make sense? I have an e to the t here. My extra piece was e to the t. So I should need t e to the t, shouldn't I? 4, 2, e to the t is a multiple of 2, 1, isn't it? It points the same way. It's always the same vector. And then an extra piece. The generalized eigenvector. Son of a bitch. It matches. This was absolute sadism. This is a sick, twisted way to spend an afternoon, man. But I did nothing more than one matrix inverse, bunch of matrix multiplication, and 2 integrals. And neither of those integrals were psychotic. They were Calc 1 integrals. I mean, here I had to do a U substitution to get the 3e to the negative t. U sub. I remember that. That was fun. And with the formulas in front of me. That's why you get a formula for this exam, people. I'm not memorizing this crap. Hit me again. What's next? An aside. We talk about differential equations and we think of derivatives d dt. We're doing all this calculus because it's continuous. But you can also think of this as a finite stepped procedure. We had water moving between tanks, right? We had electricity moving through circuits. Those are continuous ideas. But I could think of shipping behavior as moving containers from point A to point B. Physical, discrete objects. If you take the calculus idea out of this, instead of using derivatives and integrals, you use differences and additions. The whole thing still works. It's called a finite state machine or a finite state automata, and it is a difference equation rather than a differential equation. But you solve them exactly the same way. Instead of integrating, we do recursions and recursive solutions like we did in discrete, where we did recurrence relations. It works the same way. When you go to balance a tire, anybody had their tires balanced recently?
Oh, sure.
Yeah, me too. They put little weights on your tires, right? But they're little physical weights. What they're doing is they're figuring out where those weights should go to smooth out the rotation, to reduce wobble. They're taking a trig function and finding the right damping coefficients to slow that wobble down. That's a second order differential equation. But it's rotating. So they're not just doing it for just a linear behavior, they're doing it for rotational behavior, and that's a system in polar coordinates going around the axis of our wheel. it's r cosine theta, r sine theta. Or it's e to the IT. But they can't continuously adjust your wheel, so they put little discrete items on it, little sticky weights. But they're doing the same job. Finite state behavior is real world application. I got to take my car in after Thanksgiving, so I know what I'm doing next week during the break. Every now and then an application comes up, kicks you upside the head, say, hey, pay attention to this. A reminder. You can use your previous formulation. You get a new one, write stuff down, turn it in with the exam. Homework is due Friday. The review sheet key will get popped up on Friday, and we'll go from there. I'll see y'all then. Enjoy yourself.